Audio Jungle.
So now let me talk about the second module, that is rectifiers, called AC to DC converters. So in this rectifier is a power electronic device which converts AC power to DC power. The rectifiers are classified like this. One is uncontrolled, second one is controlled. Uncontrolled means diode rectifiers in which output power cannot be controlled. Fixed input, fixed output. It converts fixed AC input to fixed DC output. Whereas when you come to the controlled rectifiers, it gives controlled rectified output, controlled DC output from fixed AC input. So these are all basically SCR based converters. And again, control rectifiers, two types, half wave and full wave. We know what is the half wave, which converts only positive half cycle of supply voltage into DC form. Whereas when you come to the full wave, it converts both positive and negative half cycles into DC form. And again, full wave, two types, fully controlled and second one is half controlled. Fully controlled means full converter, half control means semi converter. So both are full wave rectifiers, but output wise these two are different. Let me see later. Another classification of the rectifier based on the number of pulses in output waveform, that is called N pulse converter. If output has only one pulse, that is called one pulse converter, and if output has two pulses, 2 pulse converter, 3 pulse converter, 6 pulse converter, 12 pulse converter, and so on. So based on number of pulses in the output waveform, the converters are classified such a way. So now let us take, this is an N pulse converter. Input is a AC input with supply frequency is Fs. It gives a DC output and the output frequency F0 is equals to N into supply frequency. This formula is very important in examinations. So F0 is called output or ripple or pulse frequency, and N is number of pulses in the output waveform. Fs is a supply frequency. So based on this formula, we calculate what is the ripple frequency or output frequency or pulse frequency of the particular N pulse converter. So this is the classification based on number of pulses and topology. Now coming to the uncontrolled rectifier circuits first. These are important in the examinations. When you come to the uncontrolled half wave rectifiers, here I am considering two loading conditions. One is resistive load, other one is a purely inductive load. These two are very important. When you come to the resistive load, this is the topology of the half wave uncontrolled rectifier. Supply voltage, here load, this is the diode. Only single. Half wave means what? Only it requires only one device, whether it is a controlled device or uncontrolled device. Here we are talking about uncontrolled, so that is why we are taking diode, which converts AC power to DC power. Here the input is AC, output is DC. So in this process, we need to analyze the load parameters. V0 load voltage is Vm by pi and I0 is V0 by R. V0 means what? Vm by pi. That is equals to Vm by pi into R. This is the output voltage as well as current quantities. A similar way we calculate what is the RMS output voltage, that is Vm by root 2. These two are derived from the basic formulas. We know how to calculate average value of any periodic signal and RMS value of any periodic signal, right? So based on those formulas, we calculate V0 and V0 RMS, average value and RMS quantity of the output circuit. And coming to the another important thing is input power factor. Input power factor means supply power factor. Supply is AC, we know that definitely it supplies the power at particular power factor, right? So that can be calculated. This is fixed in the DC domain, in the uncontrolled half wave rectifier. So that is 0.707. This is very important in the examinations. We can derive like how do you calculate input power factor? Basically that is RMS by average. Sorry, so input power factor basically what? Supply input power factor is power delivered to load by source power supplied. So V naught RMS by Vs. This is the supply RMS, this is the load RMS. By using this formula we calculate this input power factor. So what is the V naught RMS? We calculated already Vm by 2. Vs supply voltage. What is RMS? Our sinusoidal signal RMS is what? Vm by root 2. That is what we get here. It is 1 by root 2. So 1 by root 2 value is what? 0.707. In this way we calculate the supply power factor of the rectifier circuit. Fine. So another loading condition is purely inductive load. The load is purely inductive. It is very, very important. If the load is purely inductive, what is the analysis of the circuit? I have taken V1, V2 and A. These are the meters. Forget about these 3 meters first. So when you have the converter like diode as like this, diode, supply voltage and load, then analyze this circuit. By analyzing this circuit we get the formulas like quantities. We need to derive the output voltage and output current expression, right? So output current expression is what? I naught of t is Vm by omega L 1 minus cos omega t. By deriving the formula, by application of KVL to this loop and derive, we get I naught of t, that is Vm by omega L into 1 minus cos omega t. Then here when you come to the current waveform, the load is purely inductive. Current increases linearly and during positive half cycle of supply voltage and decreases linearly during negative half cycle of supply voltage, right? So increases and decreases. It would be peak at one particular point. That load current is peak at omega t is equals to pi radians or 180 degrees. So when you substitute omega t is equals to pi in this formula equation, we get I naught maximum is 2 Vm by omega L. This is the peak current of load, or I naught maximum or IL maximum, right? And when you derive, this is the instantaneous current, and derive the expression for average load current. I naught average is Vm by omega L. So when you come to the average output voltage, so here average output voltage means when you use this diode in this purely inductive load, supply voltage is positive, diode conducts and the inductor gets charged. But what about the negative half cycle? Basically diode should be off, but here what happens? Diode cannot be off because current through the load is not zero. So the same current is flowing through the diode also, right? So during negative half cycle, what would be happen here? Inductor discharges and again diode conducts. So we get output voltage always follows the supply voltage. Now V naught is equals to Vs, instantaneous value. So V naught is what? Vm sin omega t. So when you find the average value of this sinusoidal signal, that would be 0. And what is RMS? Here V naught of t is equals to Vs of t, that is Vm sin omega t. So when you find the average value, there is a sinusoidal signal, average value is 0. And what is RMS value of this signal? We know that sinusoidal signal RMS is Vm by root 2. Then what is the conducting period of the diode? So as I said already, this diode conducts continuously during both positive as well as negative half cycle. That means it conducts 360 degrees. The conducting period of the diode is 360 degrees. Now let us take the meters. Consider these 3 meters, V1, V2 and A meter. Suppose these 3 are MC type and MI type. MC means what? Moving coil, and MI moving iron. We know that MC always measures the average quantities, MI measures the RMS values, right? So now if these meters are MC and MI, coming to this table, these are all by deriving this we get these values. When you come to the moving coil V1 is what? Voltage across the diode. We know that diode continuously conducts over the cyclic period, the 360 degrees, right? So as long as diode is in conducting period, conducting state over the 360 degrees, conducting voltage drop across the diode is 0. So V1 is always 0. That is why voltmeter reading across the diode, this is the diode voltage VD. 0 if you use MC type or MI type, meter. And when you come to the V2 gives a load voltage. We know that load voltage average value is 0, already we know that. RMS value is what? Vm by root 2, already we know that. Because output voltage is same as the supply voltage. When you come to the ammeter, it is nothing but load current. Load current, this is series with the load, right? So always it reads the current. Ammeter reads current value of this circuit, load circuit or diode circuit or overall the circuit. Now ammeter reading MC meter, if it is the MC meter, that reads average value, that is Vm by omega L, already we know that. And if you use MI meter, it reads the RMS quantity, that is equals to root 3 by 2 into Vm by omega L, or 1.225 into Vm by omega L. So this table is very important in the examination, and this analysis also very important. This is uncontrolled rectifier circuit analysis. So now let me see controlled rectifier circuit analysis. Now coming to the half wave rectifiers in controlled manner. Single phase, let me talk about first, then go with the three phase converters. Now coming to the different loading conditions, the analysis of the circuits. Have not given the circuits as well as waveforms, as I am giving the formulas which are important for the examination. Just remember all these formulas. Now coming to the resistive load, if the load is resistive, which is fed by the half wave control rectifier circuit, the conduction angle of the thyristor is, basically when you go to the uncontrolled, conduction angle is pi always, but here it must be the turn on of the thyristor can be controlled by the firing angle alpha, control angle alpha. So that is why the control angle of the conduction angle of the thyristor is pi minus alpha, where alpha is called firing angle or control angle. If alpha is 0, conduction angle is pi. If alpha is greater than 0, less than 180, definitely it should be conduction angle also less than 180 degrees. Now coming to the TC is called as circuit turn off time. As we discussed already the SCR case, circuit turn off time is very important for the successful turn off of SCR in the rectifier circuits. So circuit turn off time given by the circuit when a device under reverse blocking state. So TC is equals to pi by omega seconds. Now once we get the waveforms of a particular converter circuit with the resistive load, we have to analyze the circuits waveforms. You need to find what is the average quantity and RMS quantity of the output signals. So when you come to the V0, this is called average output voltage, Vm by 2 pi 1 plus cos alpha. How we get this average quantity as well as this RMS value of the output voltage? By using the standard formulas which are discussed in the circuit theory, right? So we know how to calculate average and RMS value of the any periodic signal. By using those formulas, calculate average value and RMS value as well. When you come to the load current, this is the resistive load. In case of resistor, according to Ohm's law, what is I? V by R. So I naught is equals to V naught by R. Now what is the load power delivered to the load? P naught is equals to V naught into I naught, means RMS value of output voltage into RMS value of output current. Also it can be written as I naught RMS square into R or V naught RMS square by R. Now coming to the seventh one, this is another important thing is supply power factor of the converter. We know why we need to calculate supply power factors. Supply is AC. So the power is supplying at particular power factor. Then what is the supply power factor? That is equals to power delivered to load by power. This is power delivered to load by power supplied to the converter. This is AC power, DC power to AC power. So V naught RMS by Vs. Basically what is a P naught? This input power factor would be calculated. Input power factor is power delivered to load by input volt ampere. Supply power, load power, right? So P naught is, we know that V naught into I naught, V naught RMS into I naught RMS. This is a Vs into Is, means supply, these two are RMS quantities already. So in this half wave connection, load RMS and source RMS are equal. That is why we get V naught RMS by Vs. So by substituting these two, we get this expression. Is a very important supply power factor. So when you come to the peak inverse voltage rating of the diode, SCR in this half wave rectifier circuit, maximum of supply voltage. Peak inverse voltage rating is what? the voltage which is blocked by the device during its reverse blocking state. That is maximum of it blocks maximum of supply voltage, not more than this, right? So this is the peak inverse voltage rating of the SCR device, and this is the analysis of the half wave control rectifier when it feeds power to the purely resistive load. Now coming to the RL load circuit, basically when you come to the practical way, a practical case, all the loads are RL, inductive loads. So this is RL load called inductive load. In this, conduction angle of the thyristor beta minus alpha, because this is not pi minus alpha. In case of resistive load, this is a pi, whereas in case of inductive load, beta should be greater than pi. Device should be extended its operation up to certain instant which is greater than pi because of inductance in the load, right? So that is why we get beta. Beta should be always greater than pi. So conduction angle of the thyristor is beta minus alpha. Definitely there is a circuit turn-off time which is given by the circuit 2 pi minus beta by omega. So average output voltage and RMS output voltage both again derived from the fundamental formulas, and this is the I naught RMS and supply power factor calculation. So this is analysis of the converter half wave rectifier when power feeds to inductive load, that is RL load circuit. Now, but there are some disadvantages in this connection. Basically, what is RL load condition? This is a circuit R and L supply. So we know that some part of power will be fed back to the source. So with this, what happens? Load power decreases. When load power decreases, according to this formula, supply power, if load power decreases, this is a constant, supply voltage, supply power is always constant. So input power factor always proportional to the load power. If load power decreases, input power factor also decreases. We know that if input power factor decreases, what would be happen? Basically, the supply power also decreases, right? VI cos phi. So that is why we need to improve the load power. Means no power fed back to the source. So in order to improve the load power, in order to increase the supply power factor, connect a freewheeling diode across the inductive load, which eliminates the freewheeling diode eliminates power fed back to the source. The total power retained by the load itself. See, normally when supply is positive, thyristor in conducting state, source supplies power to this load circuit, right? And some amount of power will be, energy will be stored in the inductive case. That stored energy, without freewheeling diode, that stored energy fed back to the source. So that is why load power decreases. Now with this freewheeling diode, what happens? This power with the energy which is stored in the inductor retained by the load itself. That is why load power increases, then supply power factor increases. That is why freewheeling diode is very important in the practical case when supply is inductive load. So now coming to the analysis, this is the analysis. So when you come to the inductive load with freewheeling diode, the output voltage expression and conducting period of the thyristor and circuit turn-off time all are similar to the resistive load analysis, right? Now coming to the conduction angle of the thyristor, the thyristor cannot be extended its operation to beta as like RL load without freewheeling diode. With freewheeling diode, it would be stop at pi instant. At that instant, freewheeling diode starts to conduct. So that is why the conducting period of the main switch, that is the thyristor, is pi minus alpha. And now conducting period of the freewheeling diode, what I have taken is here continuous conduction for the sake of easy analysis. This is only for continuous conduction, not for discontinuous, right? So coming to the continuous conduction mode, the conduction angle of the freewheeling diode is pi plus alpha. It would be, see, suppose if main switch thyristor on turned off at pi instant, the freewheeling diode would be conducted up to the instant where main switch or thyristor goes to on again. The thyristor will be turned on in the next cyclic operation, that is 2 pi plus alpha, right? So now what happens? The freewheeling diode conduct from pi to 2 pi plus alpha. So pi to 2 pi is a pi, 2 pi minus pi is a pi radians plus again additionally alpha. That is why conducting period of freewheeling diode is pi plus alpha. Okay. right? So now the V naught output voltage, average output voltage, and RMS output voltage, and circuit turn off time. Now another important thing is, if you consider basically load parameters, the load quantities like I naught or V naught are not pure DC. In case of rectifier, it converts AC power to DC power, but that DC power is the DC voltage or DC current or not straight values, not ideal DC. They must have some harmonics or ripples, right? For the sake of easy analysis, I am considering a load current is a constant and ripple free current. Means constant ripple free means what? If we take this I naught waveform, this is continuous. But actually, what is I naught waveform in practical way? This is the case. So I am just taking the average of this signal. This is constant and ripple free. So when you consider a load current is I naught, that is constant and ripple free, the switch average and RMS currents. The thyristor average current is I naught into what, how much period it conducts, pi minus alpha by over the period 2 pi. So then again I naught into square root of pi minus alpha by 2 pi. Similarly, freewheeling diode RMS and average values of the currents. Now as we discussed already the 7th point, with the freewheeling diode, load power and power factor, both supply power factor both would be increased. And one more advantage of this freewheeling diode in this connection, it eliminates negative half cycle, so negative values in the output voltage. Whereas in case of inductive load, we have some negative value in the output voltage, because device would be extended its operation up to certain instant called beta, right? That is why beta is called as extinction angle. But whereas in case of RL with freewheeling diode, output voltage waveform would be like it cannot be goes to negative, because main switch will be SCR will be turned off at omega t is equals to pi instant. That is why the freewheeling diode eliminates negative values in the output voltage. That is why we get V naught is Vm by 2 pi 1 plus cos alpha. There is no beta. Okay, so this is the important thing in the examination, very important in competitive examinations, RL load with freewheeling diode. So this is complete analysis of rectifiers, half wave rectifiers with RL and RL with freewheeling diode.